Okay, now we're looking at lesson 5-1, which is page 185 in the textbook, and it's titled Factoring Integers. Let's look at the objectives that they have for it. They have the student will be able to factor integers and to find the greatest common factor of several integers. So you can see that the objective really is, there's two objectives here. One is finding factors of integers and then the greatest common factor. And the hint that, that there's more than one objective, you want to call them sub-objectives, is also indicated usually in the examples. If they give 2, 3, 4 examples, then there's usually 2, 3, 4 sub-objectives that you're looking at. And when you can do the example types of problems, that usually is a good indicator then that you've achieved the overall objective. But let's now look at the definitions. And the first one that we have here on page 185 is a factor. And it says to factor a number over a given set, you write it as a product of a number in that set. That's called a factor set. So a factor is one of two or more expressions that are multiplied together. So a factor is one of two or more expressions that are multiplied together. An example would be if I had the number 6, then 2 times 3. 2 would be a factor of 6, 3 would be a factor of 6. Okay, so that's what we're looking in terms of factor. Now a prime number, they give them in definitions usually, which will either be, sometimes you'll see them represented as natural, sometimes they'll say whole, sometimes they'll even use the word integer. But the key thought in whether they're talking in terms of natural, whole, or integer, is basically the concept of, let's just say it's a natural number. And the concept here is, has to be greater than 1. So a natural number greater than 1. That has as its factors only itself and 1. All right, so a prime number is any, or say a natural number, or you could say, sometimes I say people say whole numbers. Often they'll say integers, but now you're going to see they're restricting that integer set to greater than 1. So 1 is not a prime number. Then has as its factors only itself and 1. Right? Now we come to prime factors. Those would be factors of a number that are themselves prime numbers. And when we have two numbers, and we look at their factors, we're looking in terms of a factor that's common to both of those numbers. An example would be if we had, say, 6 and 10, and 6 we say 2 times 3, and 10 2 times 5, then 2 is a common factor to both the 6 and 10. Okay, then the greatest common factor would be the, if we had something larger, that would be products then. So if we, let's say we go to 6 and 24. Okay, here we have 2 times 3, and here we would have, say, 2 times 3 times 4. So 2 times 3 is 6. 6 times 4 would be 24. So the greatest common factor here between the two of them would be a 6. greatest common factor of them. We're not looking at prime factors here, we're just looking at common factors. All right, now let's look at the examples because that'll guide us in what we should obtain within this lesson. So example number 1 is to give all the positive factors of 57. So positive factors, so 56. So let's think about that. So positive factors of 56. Now, I like to do this with a set. And basically the elements in the set are going to be the list of the factors. And it was positive factors, so that means we're not saying a -1 times a -56 is a +56. We're looking for positive factors only. So I start out with 1. 1 times 56. Okay, that would be factors of 56. They're very, you might say trivial, or very who cares types, but that they are. Now the next thing is I see that this is, I can go to 2, and this is an even number. So 2 goes into 56. Is that 28 times? 2 goes into 5 twice, carry a 1, 2 times. 2 goes into 16 8 times, all right? Now I look and go to 3. If I add the sum of the digits here, 5 and 6 is 11, that 3 does not go into 11, so 3 is not going to be a common factor here. If I go to 4, now 4 does go into 56. So 4 goes into 5, 1 time, carry a 1, so 14. All right, 5, we can't go into 5 because the last number here is not a 5 or a 0. 6 isn't going to be 1. If it was, you would previously have 2 and 3 here. So we go to 7, and 7 times 8 is 56. Now I've listed all the factors, all the positive factors of 56. Okay, and that's basically what they're looking at in example 1. And I say it's nice to put them into a set, and then the members of the set are all the factors of 56. Now we're going to look at what's called prime factorization. And in prime factorization, we're going to take a number, factor it out so that at the end, all the factors are going to be primary numbers. Now let's look at 2 different ways of doing this. And we'll use the number they have in the book, 504. And their method of doing it is that 504 equals to, okay, the first, when you're working prime factorization, you start out with the smallest prime number that will go into the number. And we see this is an even number, so 2 goes into it. So 2 times 2, 5, 2. So 2 times 252 would be 504. And now we're going to be decomposing that, or factoring that 252. 2 goes into 252, 1, 2, 6, 126. And now we're going to take that 126, and that's going to be 63. And now we no longer have an even number, so we'll look and see, is the sum of the digits here? Does 3 go into the sum of the digits? Yes, it does. So we can go to 3 as our next primary number, and 3 goes into 63 21 times. And now we go to the next, 2 times 2 times 2 times 3. Again, we sum the digits, 2 and 1 is 3, so 3 will go into 21. 3 times 7. And 7 is a prime number. So this then comes out to be, if we put it in exponential form, this comes out to be 2, 1, 2, 3. We have 3 2s there. We have 2 3s and a 7 by itself. So that is the way the book has the prime factorization. I like myself to work the prime factorization in this type of a method, where I'll put again 2 is the first prime number into 504, and that's going to again give me 252. Then I break that out, divide 2 into it, and get my 126. Divide 2 into that and get my 63. I no longer can use 2, so I'm going to 3. And I see 3 does go into the 9 here, 6 plus 3. So 3, 21, break that out into 3 and 7. Now all along here are my prime numbers, the prime factors of 504. So I can see I have 3 2s, I have 2 3s, and I have a 7. So either method, the book method or this other method here, will give you all the prime factors of 504. All right. So that's the second objective that, or sub-objective that you have within this chapter to satisfy that, the learning objective, learning outcome. Let's look at example number 3. And example number 3 is looking at the greatest common factor. The greatest common factor of 882 and 945. So if it's going to be the greatest common factor, it has to be a factor in both Okay, it can't just be a factor in one of them. So let's take 882 and 945. So 882 and 945. And we'll start breaking this out by 2, 4, 4, 1. Uh-oh, no longer do I have an even number here. So I sum the digits. 4 and 4 is 8 plus 1 is 9. So this number is going to be divisible by 3. So that comes out to be 147. Okay, goes in 1 time, carry a 1. 4 times, carry a 2. All right, now again I look at this. 1 and 4 is 5, and 7 is 12. Hey, that's still going to be divisible by 3. And now 3 goes into 14 or 12 4 times, carry a 2. 3 goes into 27 9 times. Now I look at that and I say, if I sum the digits there, I get 4 plus 9 is 13. 3 does not go into 13. I go to 5, my next prime. It's not going to work for 5. I go to my next prime is 7, and so this becomes 7 times 7. So I end up with 2 times 3 times 3 times 7 times 7. All right, now let's look at 945. First of all, we start out and we see that it is not an even number. Therefore, it's not going to be divisible by 2. We'll go to our next prime number, which is 3. Sum the digits. 9 plus 4 is 13, plus 5 is 18. 3 goes into 18. So I'm going to be able to start out with 3 here as my smallest prime. 3 goes into 9 3 times, 1 and 5. So 315 times 3 would be 945. I look at this one. I see 3 plus 1 is 4, plus 5 is 9. So this is going to be divisible by 3 also. 3 goes into 3 1 time, 0, 5. So 3 times 105 would be 315. Now I look at this and I sum the digits. Again, that's going to be 6. 3 goes into 6. So I can divide again by 3. 3 goes into 10. 3 times, carry a 1, 5 times. Look and see some of the digits. 3 plus 5 is 8. 3 is not going to go into that. 4 is not prime. I go to 5, and I have 5 times 7. So now I have all my primes here, 3 times 3 times 3 times 5 times 7. So I'm looking for the greatest common factor, so it has to be common factors to both. I see 2 3s here and 2 3s here. I don't have a 5 or a 2. I have 1 7 and 1 7. So my greatest common factor is going to be 3 times 3 times 7. 3 times 3 is 9 times 7, which would be 63. And so the greatest common factor of 882 and 945 would be 63. Now, where in the world would you ever use all of this? Well, what about if we had 882 divided by 945, and they said simplify that fraction. Well, as soon as you got the greatest common factor to both of those numbers, you could say 63 goes into this how many times, and 63 goes into that how many times, and you probably find that 63 goes into 882 14 times, and 63 goes into 945 15 times. So the greatest common factor comes handy in trying to simplify fractions. So if we can list, and I like to put them into a set, all the factors of a number, then we are satisfied finding the positive factors of a number, like example 1. If we could do prime factorization of a number, break it down into the factors that are only prime numbers, then we're solving, that's example number 2. And the next one is if we are able to take 2 numbers, break them down into their prime factors, find primes that are common to both of those numbers, then we have what the greatest common factor is, and we can apply it in such thing as simplifying a fraction. If we do those 3 things, then we have achieved the objective to factor integers and to find the greatest common factor of several integers.